Okay, one last thing before I forget. I'm going to close the program window here and show you the macro if you want to use that to plot your results. You have the text files here in your folder, and the first test, we have the data here. We looked at those previously. The second test, it's going to just add a 1 on them. So these first tests were done, let's see, they were concluded at 5:35 p.m. The second set of tests has the _1 at the end. This was concluded at 6:49. So, about 1 hour, you have another full set of points. If you think about doing a direct shear test in the lab, that would take you several days. So here in 1 hour, you have a whole nother more Coulomb failure envelope done. So as you keep testing, you're going to get, _2, 3, 4. It's going to increment those, and then you can always look at the times of the files to know which test you were doing. But you need to keep some notes. I would keep some notes that said test depth is 13 inches here. This first test here concluded 5:35 p.m. Shear plate orientation was north-south. Second test with _1 concluded at 6:49 p.m. Shear plate orientation was east-west, and so on. Then I would go copy these directly to some other device, or USB, thumb drive, some network drive. Back them up before you go home so you don't lose them. But every time you do a test, just check and make sure the data is there. In the rare case that something happens in the program and this data is not here, you can right-click on the graph in the program and export the data. Let me see if I could show that. If I right-click, or I'm clicking with 2 fingers here, copy data, and then you can go and paste that into Excel. Sometimes that'll get you, it'll rescue the data if it's missing, or you go to export data to Excel. So, rare case that something happens, the files aren't saved, that's a backup method, and you can rescue it yourself and still save your data that way. The other thing I like to do is a screenshot. So Windows button Shift S all at once opens up the screen capture, or you could just type start and type snipping tool. Either way, take a screen cap so you see these results. Worst case, then you have at least the screen capture of what happened at the end of the test. So let me close the program. You've got this Excel BST macro here. Sometimes you may open it and it may complain about macros and permissions. You just need to let it use the macros. You may get a warning button up here. I've already clicked OK. In some cases, you may have to go to the Trust Center. In this case, I save this to the desktop, and it would actually not let me run it at all. So what I do is go to Options. I go to Trust Center Settings. Sorry, I'm getting some rain here. Hopefully it won't come through on the mic. Privacy options, or actually trusted locations. And I had to go and add a new location, and I added the desktop because that's where I had the file saved, or whatever folder you want to put that in. Then it will let this run, and it will let the macros go. I'm getting a little rainstorm here. I hit the Summarize BST Results. Would you like to create a failure envelope? Click Yes. Open failure envelope file. Okay. We'll do the second test here. Okay, I'm going to have to do this inside. Okay, I made it in from the rain, so let's try this again. Just to show you what you can do with the BST Excel macro. You can always import the data and do what you like with it, but this macro will kind of quickly get you a graph, and then you can further modify it. So I click Summarize BST Results. It asks, would you like to create a failure envelope? I click Yes. Open failure envelope file. Okay. Go to the folder we saved everything in, which is temp, and we're looking for the text lab view measurement, or LVM files here. The first test we did had nothing on the end except LVM. The next test we did had an _1, and if we did a third test, it'd have an _2, and so on. And you can also see the time this file was saved, 5:35 p.m. when that test was concluded. And then the next test, the second one, has _1. That test was finished at 6:49 p.m., so about an hour later. So we're going to select the failure envelope from the first test here. Hit Open. Would you like to create a shear stress history? Usually you would. So click OK, open the shear stress file, make sure it corresponds to the same test, so without the _1, and it's going to do some macro work here, kind of extend the columns or delete all the zeros at the end of things, so we're only plotting the actual data. And then it says open displacement file. So at this point we're currently fixing a bug in the program, and the displacements are all 0. But what you can do that's perhaps even better is plot it versus time, exactly like you saw on the screen during the test. So instead of displacement file, I click OK, but instead of opening the displacement, which would be here, stepper displacement, I'm going to click time. This stepper displacement file is full of zeros. And I'm just going to change the axis to say time in seconds instead of displacement in inches. So this one does the macro things, and then down here I'm just going to double click, replace this legend here, Control A, and say time in seconds. And this is the data that you saw on the screen there. And remember, EU here is engineering units, so you could go through and edit these and change to KPA. But I will, if you go right click, or for the tablet, 2 fingers, select data, you can edit all of these, and let's see here, you can change these series names and replace the EU with KPA. So series name here, you could say 60 KPA normal stress. But that's a little bit laborious. I'll show you, change that one there. We can go through and quickly replace all the EU with KPA in the text files first, and it'll save some work here. Here the y-axis, even if we had searched and replaced in the files, we'd have to change this here to KPA. And yeah, I guess there is a space there. So your shear history there, you can plot that, you can compare it to other tests, and really this displacement, you might want to just rename that time. So that's one plot, the stress history. The other one that's useful is the actual failure envelope. I'm going to not save that. And so here's the default failure envelope, normal stress. Again, you could replace all the EU with kilopascals in this case. Probably the next version of the program, we will just hard code kilopascals, because the units we're producing now are pretty much done in SI units. So this will save you some work in the future. Here you get the regression line here, and by default it just includes all points. So if I wanted to if I wanted to get the friction angle, I'd take the inverse tangent of this slope here, 0.7927. So if I go over here, I can actually click on the text options, the label options actually, and this last icon over here, change the number category, and then select a number of decimal places. If I want one more decimal there, I could use 5. And then here I could calculate equals a tan of that slope I see up there, 0.79272. And by default, in Excel that would be radians, so times 180 degrees over pi. And so then the friction angle there is 38.4 degrees. So we don't really report friction angle to nearest decimal, usually the nearest whole number, but we'll just have one decimal point here. So 38.4 degrees, and then this case, it's using that first point that had the partial seating problem, which is dragging the overall slope down. And even the last point, we kind of went pretty far, and maybe that was shear head fully expanded. This point seems like it's kind of starting to fall away from the line. So we could omit those two. You could select the data points here, and then when the input data is highlighted, you can just say I want to get rid of that first point, and say I wanted to leave the last point off if I thought that was the shear head was fully expanded there, and then just include these in the regression. Then we get almost 0 here. And then if I double click here on the regression line, let me do that again, double click on the regression line, I could project backwards. I want to go back to 0. So this first stress is 60 or 59.3, So I could project back 60, and that's going to go back to 0 there. I can set the intercept if I want to force this through 0, and then I've got this slope here, and we can fix these axis limits to not be negative. We just make that 0. Double click on the x-axis, make that 0. And there we go, a little bit better looking data. And then it's always a good idea to plot those other data points back in there. So I would select data by right-clicking on the chart, add, and then I'm just going to hit tab, go down and select the X, hit tab again, select the Y, and hit OK. And so there's that first point. You can see that it's definitely below the line. So it definitely appears to be the partial seeding problem. And this data is pretty much telling us that there's 0 cohesion in the soil. So if I if I use this slope now, forcing through 0, the slope is 0.77013. Let me see how much friction angle would change in that case. 0.77013, 37.6 degrees. So pretty much both of those rounded give 38 degrees. So for this soil, I'd probably say 38 degrees friction angle and cohesion 0. Let's see. You can save a lot of time there if you want to kind of search and replace in the files first. So let me show you that. And actually, before I do that, let me show you. I've already kind of processed both of those files there, and got them to a little bit more presentable state. So if I go to let's see, test number 1, shear stress versus time. I just changed the title to shear stress versus time rather than shear history, I think it said. Stress history has a specific meaning in geotechnical engineering, so shear history is not really that accurate. Shear stress versus time is what the plot is. And then over here, you may want to actually plot versus the real normal stresses. These are sort of the nominal values. But remember, this was maybe 29.9, 59.8. The later versions will actually use those measured average values, which you have in the other file, the one for the failure envelope. But just versus the nominal values, these were our target values there, and we were all within 1 or 2 kPa of these values. The next macro file, as we update, will actually use the average or the measured values, and that's actually done in the MATLAB subroutine that's mentioned in the user manual. If you download that, MATLAB also just takes the average normal stress measured during the test and actually uses that in the graph legend here, just if you want to be a little more precise. So I did that for the 2 files, the 2 tests, but then looking at the failure envelope, did a little more processing here, and okay, so in this case, just examine what does it look like if I do not use the first point because of partial seeding. So I just made that a separate series on this plot, and then this last one here, due to full expansion of the shear head, it seemed like it was started to fall away from the line, and that's a separate series on its own. So usually we like to plot those points as open symbols, meaning they're not included in the regression, and then we extend the regression backward and forward to see are these points kind of falling away from the line. So here 0.99996, 4 9s and a 6, really good linearity there. So I think that's pretty reliable results. And this is the slope, 0.77013. Over here, there's some built-in MATLAB functions. Intercept, slope and intercept will give you, the slope intercept form. So the intercept here is the cohesion. So you notice I'm using just the data without the first and last points, just like the regression line is actually now using in the figure. This is just doing it in cells. Calculation-wise, if you wanted a formula, you could cut and paste and just use this in other spreadsheets. So here I have the slope function built in from Excel. Slope, it's slope, known y values and known x values. So again, the same group. And then that's in radians, so multiply by 180 over pi. So arc tangent of that slope times 180 degrees over pi. So 37.6 degrees, pretty much the 38 degrees we had before. But here, the r squared is 0.9997. And then if we force C equals 0, we would get this arctangent of 0.77013, what we actually see in the figure's regression line there, right? Because that's, it's just using these solid points. It's not using those others because those are not included in that series, right? That's plotted here. So that would be 37.6 degrees. So basically the same as over here. Which this one is, slope intercept is not forcing the intercept equal to 0, and you have some tiny negative cohesion, minus 0.2 kPa, so it's essentially 0. So go ahead and force it to 0, doesn't change the phi. And then this, just a note, test depth 13 inches for that depth of the shear center of the shear plates. North-south shear plate orientation, and then test 2 was east-west orientation. And then first point was ignored due to partial seating, last point ignored due to full expansion of shear head. Did a similar thing for the second test, and actually even brought the data in and compare them. So here's the second test. In this case, there was a little more variability, more distance away from the line for these points. So the R squared dropped a little bit, 0.99857, still 0.999, still pretty good. But if we drop that first point due to partial seating, we get 33.2 degrees. So 33 degrees here, and was it 38 degrees for the other one? A little bit of difference. If we had more time, we could do several more tests and do some different depths, and repeat this around the yard, and maybe get some even better agreement. But overall, we applied these normal stresses and measured these values. Pretty good repeatability, but it looks like there was a little bit of difference there in the two directions. Like I said before, any gravel particles like we encountered when I was augering, if they happen to be at the depth that you're testing and they contact one of the shear plates, they will affect the results and sort of raise the stress. This case, that might have been we might have been suffering a little bit from that, but you see what you can do with the data here. One last thing, say I wanted to kind of process this quicker, then I would make a new folder and copy the files in there. So I'll say EU, I already did this once, but let me say EU replaced with kPa. And I take those LVM files, just copy them all, Control C, go in here, Control V. They're all highlighted. If they weren't, I would just click Control A and enter, or open, either way. And then I'm going to hit Control F is fine, but I'm going to hit Control H, find and replace, and I'm going to replace EU with kPa everywhere. So I say replace all, close that file, and it'll say, do you want to save? So I just hit enter, and it saves it. And I'm now at the next file in line, towards the end, replace all, close. It doesn't ask me, that means there actually was no EU in that file. So replace all, close, replace all, close, save, replace all. So just repeat this for all the files. And if you're handy or you use Linux or Unix, you can even write a shell script to do all this for you. If you're using the MATLAB routine, then this is even easier. We don't need to do all this stuff. Sorry. Replace all, close. The tear files don't have it, so that's not necessary. And the displacement, the last one, say yes. Okay, so every instance of EU, at least in our text files, has now been replaced with kPa. So normal stress, 120 kPa, makes things a little easier, a little quicker as far as using the macro. So then if I did the macro, and I selected those files, we'll see we only have to change EU in a few places now. So would you like to create a failure envelope? Select file. We're in temp, EU replaced with kPa, failure envelope, first one. Shear stress history, yes. Open file. Shear stress first test. It's doing its macro magic here. And displacement file, remember we're going to replace that with time. Plot it versus time on the x-axis instead of stepper displacement. Time may be, more meaningful. So again, just replace the x-axis label here with time in seconds. But then you see all these at least now are kPa. You don't have to do any replacing there. This one we can, double click, do that one pretty quick, and then that save you a bit of time there. And then let's see the. I'm going to close that. Failure envelope file. Still have to replace EU, just 2 places there with kPa, but otherwise kind of saved us from some time. One last comment. So the program measured the initial values of the shear stress on channel 1 and the normal stress on channel 0 when the test started, and there was no gas pressure applied, but there was a small noisy voltage, just the electrical noise level of the instruments. And that was something like 1 kPa, really small value. So it took that as a tare value that it subtracted from all subsequent readings. The shear stress, it did the same. It actually took that shear stress tare value at the start of the test, which corresponds to the weight of the shear head and the rods hanging from that plate, which is causing it to have some reading. It was like 3 or 3.5 or 4 kPa. That number is going to go up as you add rods. You definitely need to do that. There's another phenomenon that when you open the shear head, it's got a little bit of friction, and you need about 0.5 to 1 psi of pressure before that shear head will start to open and overcome just the friction in the O-rings that are keeping the oil in there. So what you could do is subtract a 0.5 psi to 1 psi, so something like 4 to 6 kPa of normal stress as a tare, another tare value for that opening friction, because that's not necessarily applied to the soil. It's needed to overcome the friction to move the piston. So what that would do is it would, for all your measured normal stresses here, it would just shift them to the left by about 5. And it would not change the slope. It does not affect the friction angle at all. All it does is affect the cohesion a little bit. And this is one of the partial explanations why you may see some negative cohesion. Well, if you want to be more precise, I'd say equals this minus about a 5 to 6 kPa. 6.79 kPa is 1 psi. If the opening, you can measure this yourself on your unit. See how much normal stress it takes before the shear head first opens, but let's say that was about 5 kPa. So I'm going to say take that value minus 5, and I'm going to copy that, and then if I just copy and paste as values, it'll just replace these x's in the plot. So let me say paste special as values, just this one here. So every point just shifted to the left a little by 5. So there's a physical reason for that. It's that opening friction. That the actual normal stress applied to the soil is somewhat reduced from that because of that opening friction. So if you're really splitting hairs or looking, at a small cohesion value, then this could be important. It's not going to change the friction angle at all. So that's what you can do with the macro. Otherwise, do as you like with the data. There's a MATLAB subroutine if you're using MATLAB. That's also available in the user manual. There should be a link to it so you're able to download it. And please give us any feedback that you have on, we can incorporate necessary changes into future versions. So happy testing. Thanks.